Molality and colligative properties activity. And let's go to a screen share here. All right, so we're going to look at colligative properties. And when we do colligative properties, mathematically, we have to use a term called molality, which is very similar to molarity. Here's the distinction. Molarity is moles of solute per liter of solution. Okay, what is molality? And that's represented with a small m instead of a big M. It is the concentration of a solution in moles of solute per kilogram of solvent. Okay, a kilogram of solvent, if you think about the density of water is 1 gram per milliliter or 1 kilogram per liter, it's really 1 mole per liter, but instead of 1 liter of solution, it's 1 liter of solvent, or like water added, if that is our solvent. So if I were doing a 1 molarity solution, I put 1 mole in and add enough water to get to 1 liter. If I did molality, I put 1 mole of solute in and actually add 1 liter of water. So because I'm adding a little bit more water when I do molality, then molality will be more diluted or have a lower number than molarity if I have 1 molarity versus 1 molality. So 1 molality is less than 1 molarity. If it's a dilute solution, there's very little difference. If it's a highly concentrated solution, that difference can get quite large. Okay, why do we use molality? Molality mathematically links colligative properties better than molarity. So it's an offshoot. Most of the time we're going to be using molarity, but we will use molality just for these things called colligative properties, and more on that in a bit. Let's just look at some calculations here. I will take a quick break to let the dog out and be right back with you. Here you go. My doggy break is sponsored by IAMS, Healthy Dogs. Okay, sorry about that. Calculate the molality of 1.5 moles of CO2 in 355 grams of water. Oh, molality is moles over CO2 over kilograms of water. That will be the solvent that we'll use in all of these. And 355 grams is 0.355 kilograms. So 1.5 divided by 0.355 gives me 4.2. Okay, what if I'm asked for the molality in 146 grams of NaCl in 2.5 liters of water? Well, if we got grams, we can convert to moles. And if we have liters, we can convert to kilograms. And if 1 gram is 1 milliliter, then 1 liter will be 1 kilogram. So 2.5 liters is the same as 2.5 kilograms. With that, we can just take our moles over the kilograms and figure out the molality, and I'll use a small m for that. Okay, as far as colligative properties, they depend on the number of solute particles, but not on the identity of a particle. And two of the ones that you're going to look at is freezing point depression and boiling point elevation. So this is how freezing point depression works. We have this formula, triangle TF for freezing. The triangle meaning change in temperature is equal to I, KF, which is a constant, and then molality. Okay, and the KF factor for water is negative 1.86 degrees Celsius per molality. All right, let's take a look. What is the I factor? That's how many particles are present. If it's NaCl, it breaks up into Na plus and Cl minus, so that I factor is 2 because it breaks into ions. If it were like sugar, which doesn't break up into things, then it would have an I factor of 1. If it would be CaCl2, which breaks up into 3 particles, it would have an I factor of 3. Okay, we know what Kf is, that's given. And then we're given moles, we're given grams, so we can ultimately figure out the molality there. And then we just take that and punch that in. The change in the freezing point is 2 times the negative 1.86 times the 3.64, and it gets to be 13.5 degrees Celsius. So what's going to happen is the freezing point is actually lower. And I probably should have put a negative sign in front of that. I realize I didn't do that, and I should have. And what's the change in the freezing point? Let's see if I did it here. Okay, it ultimately becomes, it goes from 0 to minus 13.5. Now, again, 0 would be 32 Fahrenheit, and minus 13 in Celsius is about 25 degrees Fahrenheit. So you'd be going from like 32 down to, what, maybe, in the single digits, which is why it explains they might put salt on water. It drops the freezing point, keeping it in the liquid state longer. Okay, let's go to another example of boiling point elevation. The boiling point of a solvent is raised, doesn't say that here, when a solute is added. Here is our formula, and this is the KB for water. Notice there's a positive sign there. It actually raises the boiling point. And the other one was negative 1.86. This is smaller by a factor of what, 3 or 4 times smaller. Okay, if I look at this problem right here, I talk about 220 grams of CaCl2, 1.5 liters of water. I take my I factor, which is 3 because CaCl2 breaks up into 3 ions. I take my Kb and I figure out my molality. And again, I can just take my moles divided by my kilograms, which is the same as my liters, and I get this number and punch this in, and I get 2.03. Okay, so not that big of a change, but the new boiling point goes from 100 to just over 102. So that would be an example right there of how to apply this. Okay, when you get to your assignment, you'll have some things where you're just asked to figure out molality, and then you'll have to solve things, and these are all the things there. Colligative properties, the 2 we're going to look at is boiling point elevation, freezing point depression. There's something called vapor pressure lowering and osmotic pressure, which we won't look at. But they depend on the number of particles at I factor, but not the identity. So in other words, KCl and NaCl and KNO3 and NaNO3 would all have 2 particles or an I factor of 2, so they should all behave the same. Okay, just one extra bit about, looks like I need to let the dog in, and then I'll just close with a little bit about the boiling point and freezing point qualitative. Yeah. Okay, boiling point. Why does a solution boil at a higher temperature than water alone? Well, when salt is dissolved in water, like NaCl or CaCl2 or anything, the water is the salt is almost like glue holding it to water. Now, if I boil salt water, what's going to actually boil off will be just the water. And it's more difficult or takes more energy to boil off that water when that water is attracted to salt water or to the NaCl or CaCl2 particles. So in other words, those particles, those ions of the solute, hold the water and make it more difficult for it to boil off. And that's why the boiling point is raised for a solution. Okay, why is the freezing point lowered for a solution? Really the same reason, that salt, which whether it's NaCl or CaCl2 or whatever's in there, is going to stick to the water. And when salt water freezes, it's actually the water that freezes out. And in order to get it to freeze, you actually have to bring it to a lower temperature to get the water to freeze out, because that salt and water is attracted to each other. So because of that attraction between the solute of the salt and the water, it makes the freezing point lower because it holds it like glue, and it makes the boiling point higher. That's why we get a freezing point depression and a boiling point elevation. And the rest of it is just a numbers thing to figure out the quantity of that. Thanks for watching.